All right, let us begin. Welcome to CS4510. The topic, this is what, L11A. The topic of today is going to be called Foundations of Mathematics. Foundations of Mathematics. This first half could have really been called anything. We are at a turning point in the course, and we need to discuss a topic that will take us over 2 lectures. Sorry, slightly under 2 lectures. But one of them is, we have an extra lecture basically. We only need like half of a lecture, so we're just gonna use that half now, and then we're gonna have the next 3 lectures. This first half is just gonna set the tone for the next 3 lectures. And again, this is like, I think the most important sequence of lectures in the course. This is basically the whole reason you take the course. So this first part is just history and setting the tone of this. We're going to discuss basically an unsolved problem, an arc in history that spans millennia. It starts 300 BC and it ends in 1936. And such a program has, religious origins and so on. Recall what we did last time, and today is mostly a history lecture. What we did last time was we talked about Cantor's theorem, which is that the cardinality of any set A must be strictly less than the cardinality of its power set. So there, among other things, there is no set of strictly largest cardinality. And in fact, this is true even for infinite sets. So that for every set that is infinite, there is another set which is infinite as well, but larger. And that kind of contradicts our notions of intuition about what infinity really looks like, because it's like, mathematics is supposed to correspond to, formal notions are only supposed to correspond to intuitive ones, in the sense that we do something formally because it's true intuitively. Something like this. But here we have a demonstration of a theorem which is true formally, but what does that mean intuitively? We really don't know. So there's a lot of schools of thought that spring up in rejecting this, figuring out ways to say that this is actually wrong, only because it doesn't make sense to them. We'll discuss that, how that falls into what we're just talking about later. For now, let's start at 300 BC. There was a guy who lived 2,200 years ago, whatever. His name was Euclid. Euclid wrote a book called Euclid's Elements. Have you heard of Euclid's Elements before? It was something like 9 treatises on geometry and other subjects. He described what we would now call today Euclid's algorithm, properties of the greatest common divisor. But important there was basically the origin and the foundation of all of geometry. And he gave he was the first to begin with, most formally so, the axiomatic method. And the axiomatic method is really the point of Euclid's Elements rather than any specific geometry. What is the axiomatic method? What is truth? What does this mean? So truth is something that we all kind of know, but we don't really know how to describe. It's such a concept, and formalisms of it do exist. But how is truth learned or discovered or gained? And there are several perspectives. One of them, in a physicist sense, is that you have a set of truths which sort of balance each other out in equilibrium, in the sense that one may show the other, and then that may show it. And then everything just kind of holds itself together through a net. But the axiomatic method is really due to Euclid in the sense that truth may only be derived from other truths. And those truths may only be derived from other truths. And those truths, again, derived from other truths. And so you rewind yourself backwards through this sort of giant tree of knowledge. Those two are used to prove this thing, and then that's used to prove that, and that, and that. And then you rewind yourself up, and you are at a foundation known as the axioms. And the axioms are truth, which is defined to be true, and that's it. They are given to you by God. There is no questions. They are true, period. And then only from the axioms and the laws of thought, the rules of deduction, may you derive new truth. And the laws of thought are themselves axioms, how to produce new truth. So Euclid gave an axiomatization of geometry. But what really is geometry? Geometry is a human experience. It's the way Euclidean geometry explicitly is the way we interact with the world in 3 dimensions. You know, we have right angles, or we have notions of orthogonal spaces, and so on. The axioms specifically were as follows. So first he defined some of the objects that he used. The objects, importantly, are points and lines. So let's just pretend we're in 2 dimensions for now, because that's the only case that really matters. You probably know that the dictionary cannot define a word in a recursive way that uses the word in the definition. You want to avoid this. So what is a definition of a point then? Euclid's definition is that which has no part. And then the definition of line is that which has no breadth. That's honestly about as good of a definition as you could give for what these are. We know what a point is and we know what a line is, but you want to delegate to some formal definition. You don't want the discovery process of truth to be delegated to some intuitive principle. You're like, yeah, I know what a point is. Yeah, I know what a line is. That's not how proof is done. You want the proof to be done fully axiomatically to the axioms from the formal system, from those laws of thought, and not to any intuitive notion that you have that may be unstated. The first 4 postulates in his book were as follows. 1, any 2 points may be connected by a line segment. 2, any line segment may be extended in both directions. 3, for any point and radius, there exists a circle. 4, all right angles equal each other. Okay, so the postulates, these are the first 4 postulates of Euclid. They ought to be so simple that you could not take one as theorems of the other. And a statement, what's the difference between a theorem and an axiom? A theorem is that which can be proven, and an axiom is that which is assumed to be true. So if something can be proven, why take it as an axiom? Just take it as a theorem. So we would hope that the axioms be so simple as to model all theorems that are true and nothing more, right? These 4 axioms specifically constitute a version of Euclidean geometry known as neutral geometry. And again, the point is not that, the point has nothing to do with geometry. This is not really a lecture on geometry. It's about the beginning of a history of this program of rationality, right? Ancient Greek philosophy is not something particularly impressive or unique or anything like this, because it's true that you could all rediscover things yourself. And Euclid's Elements really are perhaps the canonical example of this study which extends something called Plato's theory of forms. So Plato, again, and also an ancient Greek man, probably knew Euclid through grandchildren association, something like this. Plato's theory of form, so what is Platonism? Does anyone know a definition of Platonism, or even Neoplatonism? Platonism is this idea that things exist independent of the real world. This is maybe not the best definition, but you have to take Platonism as, you believe Platonism to be if you are a mathematician, you have to take some form of Platonism, in the sense that there are abstract ideas totally independent of reality. Plato specifically was obsessed with this theory of forms, in which he tried to create a very rigorous dichotomy of everything, of all objects that could ever exist. And he specifically created this distinguishing notion of the ideal and the real. So all objects could fall upon a dichotomy, in the sense that he was creating a directed acyclic graph of every object, everything. And for example, there existed in the ideal world concepts that were pure and immaterial. And in the real world, there existed things that were real, material things, sheep, animals. And the ideal world was like, for example, there may exist the form of beauty. And then from the form of beauty, you may derive the concept of beauty. And then from the concept of beauty, you may derive objects that are beautiful. And as you make such derivations, you get more and more applied and less ideal. So everything exists on this directed acyclic graph, of which there are objects that are more pure and less pure. In a classic example, mathematics is incredibly ideal, and something like biology may be very real, and then in between you could have physics and chemistry and so on, right? Not only was this dichotomy the theory of forms by Plato, but in fact, something much stronger could be said, which is that the only way to study notions of the real is to study notions of the ideal. So let's say you want to study triangles, right? Everything in the real is simply an approximation of things that are ideal. So there exists an ideal triangle. It's immaterial, it's purely perhaps mental, but it is independent of any specific physical, material instantiation of a triangle. And the real consists of things that are error-prone and approximate. You may arrange 3 sticks to form a triangle, or you may draw in the sand a triangle, but all of these are simply approximations of the ideal triangle, right? Which is so pure it could never be brought into the material world. Something like this. More strongly, you cannot study the real itself. You cannot study a bunch of approximate triangles to understand what a triangle is. You must study the ideal. And this is, again, why if you are any sort of mathematician, you must take some form of Platonism, because we only work on abstractions, right? Not everyone agrees with Platonism. There are many more modern schools of thought that are like the real and ideal shake hands, and then they may influence each other's designs, whatever. But this is just what Platonism is. And specifically, it is the case that Euclid's Elements is such an instantiation, right? Geometry, again, very real experience. It's part of the human. The human experience is to experience geometry. The walls of this room appear orthogonal to me, right? The floor is perpendicular to the walls, and the ceiling is parallel to the floor, and so on, right? This is human notions, cognitive ones. But we would hope that from these sets of axioms, we may derive ideal theorems which can implicate real ones, right? Whether or not we take an actual parallel bubble meter and try to see if the floor is actually parallel to the ceiling. Right. And again, this is about rationality. And rational arguments are actually relatively new in the scope of human history. You guys heard of Abraham Lincoln? You guys heard of John Brown? Maybe. So I have a quote by Lincoln here. So before just because calculus had not been invented yet did not mean you did not have to take math courses. So back in the day, you actually had to take a 3-course sequence in Euclidean geometry, where you did extremely tedious constructions using the axioms. And such constructions include, using a compass and a straight edge to draw, a hexagon or something like this, only following such simple rules. To circumscribe a quadrilateral inside a circle. Such things that can be done. But here's the quote by Lincoln. So, at last, I said, Lincoln, you can never make a lawyer if you do not understand what demonstrate means. And I left my situation in Springfield, went home to my father's house, stayed there till I could give any proposition in the 6 books of Euclid at sight. I then found what demonstrate means and went back to my law studies. So, the point is deduction, in the sense that an application, a sequence of axiom applications, gives you the truth of a proposition, in the sense that you demonstrate it to someone else who may verify your proof, right? And I'll give you, here's another unpublished note. If A can prove, however conclusively, that he may of right enslave B, why may not B snatch the same argument and prove equally that he may enslave A? You say A is white and B is black. It is color then, the lighter having the right to enslave the darker. Take care. By this rule you are to be slave to the first man you meet with fairer skin than your own. You do not mean color exactly, you mean the whites are intellectually superior to the blacks and therefore have the right to enslave them? Take care again. By this rule you are to be slave to the first man you meet with an intellect superior to your own. But you say it is a question of interest, and if you can make it your interest, you have the right to enslave another. Very well, and you can make his interest, and if he can make it his interest, then he has the right to enslave you. So what this really is not a moral argument against slavery, of which there are numerous ones. This is a logical argument against slavery. And the difference here between these is that there exist many, many moral arguments against slavery, but here what Abraham Lincoln is doing is giving a fully logical argument against slavery. He's appealing not to a sense of morality or anything, but to the logos. In a purely analytical, deductive sense, slavery is wrong. Not that it is immoral, but that it is wrong, right? An example of for example, a moral argument against slavery would be John Brown. John Brown was also an abolitionist. He thought himself like a weapon of God, a divine instrument, and he got a bunch of guns and rounded up a bunch of people and said, we're going to start shooting slave owners. So, Bleeding Kansas, he was put down for it, and it's the start of the Civil War. But it's the kind of, there's a difference in thought here, is what I'm trying to demonstrate. In the sense that John Brown, we could say, perhaps acted morally, but not logically. But Abraham Lincoln gave a logical argument. That is a relatively new concept in the history of humanity, and don't take it for granted that we've only been doing logical thinking for a few hundred years. Humanity's existed for several thousand. Most of the arguments have not been from a pure logos standpoint. They've been poorly argued, some through morality and such things, right? So this is really where we are. Any questions so far? Okay. So let's talk a little bit more about Euclid's elements. There was the 5th postulate. The 5th axiom of Euclid is as follows. For a line L and a point P not on L, there exists exactly one line through P parallel to L. So what he's saying here is take a line L and let there exist a point P which is not on L. There exists exactly one line through P which is parallel to L. Okay? Is it the 5th postulate true or false? There are 2 answers.
I'd say it's true.
Why?
From looking at it, it also makes sense that if it's parallel to L, it must be, if it goes through P, there can't be another parallel line that also goes through P because it would be on top of the new line.
So that's one of the better answers, is that it sounds right, is basically what you're saying. Like that, what you're trying to say is that corresponds to my intuition about how geometry works, about my understanding about how ideal lines and points work. I mean, that sounds right. So That's good enough. And by the way, what would a definition of parallel be to Euclid? Maybe 2 points. 2 lines are parallel if they share no point. You can prove, for example, in Euclidean geometry, if 2 lines share 2 points, then they share all points. Something like this. And the definition of line, of course, must exclude things like curves and so on. But so that's one argument in favor. The other argument in favor is not in the sense that it corresponds to the intuition, but from a purely logical standpoint, it is by definition an axiom, so it must be true, because we're assuming it to be true. That's perhaps the worst answer. The better answer is that it is an axiom because it makes sense. That's the thing. So people spent several millennia studying Euclid's Elements. It was translated into Chinese, into Arabic. It was studied around the world. It was distributed everywhere. And after several millennia of studying it by many people, it came under some scrutiny because it's like, are these good axioms? And that's kind of an interesting question. The first 4 axioms are so simple, they may not be argued with. I mean, number 4, all right angles equal each other. I mean, like, if you don't have such an axiom, certainly such a system is probably useless. But note that you could not assume it if you were missing the 4th postulate, right? You could not prove that. The 5th postulate is unique in the sense that it's totally, like, different than the others. It's the first one that seems complex. It's non-trivial. This is different. So the question is the 5th postulate really necessary? So for any axiomatic system, let's say AS, and let's say T is a theorem, we may write that the axiomatic system proves theorem T. And we use this symbol to note that this set of axioms proves T. And this notation means that T can be demonstrated, provably so, through the axioms, in the sense that there's a sequence of applications of laws of thought and whatever that the axiomatic system can prove. So the first questions people had is like, is this a necessary axiom? Can you take it as a theorem from the other axioms? And by the way, these are the first 4 postulates. There's books and books of them, of other things. There's chapters on projections and circles and so on, right? So the first question is, let's suppose we take Euclid's Elements and we remove the parallel postulate. If the parallel postulate is necessary, then it should be the case that we cannot prove the parallel postulate, assuming we do not have the parallel postulate, right? So the question is the parallel postulate necessary as an axiom, or is it, can it be a theorem? So if you could prove the parallel postulate from the remaining axioms, then don't take it as an axiom. It's okay to take it as a theorem. And the term here is independent. And with respect to a vector space, you understand a vector to be independent of a basis, or something like this, if there is no linear combination of such vectors, right? It is orthogonal to them in some sense, right? And we use the term independent here. Is the parallel postulate independent of Euclid's Elements? In the sense that the answer is actually yes. This is very difficult to show, but we know that you cannot assume the parallel postulate as a theorem of Euclid's Elements. You must take it as an axiom. It cannot be demonstrated from the other 4. And that may be a little obvious because, I mean, nothing there tells you how to demonstrate it, really. It's not an immediate corollary. Okay, so if it is true, it must be an axiom. The second question, is it a good axiom? And to answer this, we would ask, if you were to take Euclid's Elements, remove the parallel postulate, and then add in a negation of the parallel postulate, is it the case that you prove contradiction? For example, 0 equals 1. 0 equals 1 is the canonical contradiction. It's the smallest contradiction in some sense. Now, an axiomatic system must only be able to derive truth. And if you have a system which can derive some statement to be true and false, the entire notion of truth is itself vanished. It's gone. It's not the case that you may have one simple theorem which is both true and false, and it is off in a corner by itself, and the rest of truth is consistent for the other theorems. If you have any single theorem that is both true and false simultaneously, then all of every theorem is both true, and every theorem is simultaneously false. You can in fact prove and disprove everything simultaneously. Everything black holes into meaninglessness, and you're gone. So if this would be the case, we could take this as evidence that the parallel postulate it's a good axiom. We would be like, all right, I'm confident that is necessary for Euclidean geometry and is a core point. Now, the point of today's lecture is that, like, what happened is if you took the negation of the parallel postulate was very philosophically not so good, because it turns out that this is false. If you assume the negation of the parallel postulate, you do not derive an inconsistency. What you derive is something far more interesting. So what is the negation of the parallel postulate in pure logic?
Is it the formation of the negation?
Yes, what would the negation of the parallel postulate be?
For a line L and a point P non-L, there exists multiple.
Yeah.
None.
So let's just give you a quick example of what that would look like. So in fact, we take the negation twice. Consider that we have exactly one line through P parallel to L, okay? Suppose we take the parallel postulate in an unnegated form. We get all the theorems of Euclidean geometry. We get, for example, given a line L and a point P not on L, there exists exactly one line through P parallel to L. We can also prove that the parallel postulate is in fact equivalent to the interior angle sum of a triangle. What is the interior angle sum of a triangle?
180.
Yeah. Right. All the other terms that you may know from Euclidean geometry. Now suppose we take the two different negations of the parallel postulate. If it's not one, we actually have two cases. The first case is that it's less than one. And the second case is that it's greater than one, right? So let the second case be for a line, suppose we take the negation of the parallel postulate to be for a line L and a point P not on L, there exists 0 lines through P parallel to L. So it is impossible to construct parallel lines. What this really tells us is that we get a model, what's known as a model of Euclidean geometry. A model is, by definition, there's kind of a complex definition, but you may understand a model to be the theorems that are true given a set of axioms. So every set of axioms, if there's no contradiction, instantiates some model, right? Some set of theorems that to be true. The set of theorems that are instantiated by Euclid's elements with the negation of the parallel postulate do not give you an inconsistency. They give you a consistent model of geometry that is simply alternative. So the definition of line, as Euclid uses it, actually can correspond to what's known as a great circle of a sphere or an ellipsoid. And a great circle is that which is basically a circumference of maximum length. Any tiny circle else would be considered a curve under Euclid's definition. But to consider any two great circles. No matter how you put these great circles, no matter which great circles they are, it must be the case that they intersect in 2 points, right? So any two lines must intersect in at least 2 points. They may intersect in infinitely many points if they're the same great circle, but no matter how you put these great circles, they must intersect in 2 points. Also, it is not true that there exists a triangle of 180 degrees. And in fact, you can construct a triangle. Any triangle in spherical geometry has strictly greater than 180 degrees interior angle sum. And in fact, it has 180 degrees interior angle sum if and only if it has area 0. But then that's not a triangle, it's a point. So let's give you a triangle of 3 right angles. Begin at the North Pole, okay? Let this be this. Begin at the North Pole, walk to the equator, turn left. Walk a quarter way around the equator. That's a right angle. Turn left again. You are now back at the original. This is an interior angle sum of 270 degrees. Okay. So on a sphere, you can construct a triangle of 270 degree interior angle sum. And in fact, the smaller the triangle gets, the closer it gets to 180. You can perhaps believe that because the smaller the triangle gets, the flatter it gets. But of course, it'll never be purely flat, right? So every theorem in spherical geometry is almost one in Euclidean geometry, but everything is slightly perturbed. It is not the case that any theorem is false. Like, you don't get the fact that, you don't get a contradiction here. You just get an alternative model of truth. Similarly, suppose if we take the negation to be there exists greater than or equal to 1. So suppose we took the negation of the fifth postulate as an axiom to be for a line L and a point P not on L, there exists strictly greater than one line through P parallel to L. So what that means is given a line P and a point, given a line L and a point P and not an L, sure there exists this one, but there also exists this one and this one, right? And so on. This ends up modeling a kind of geometry, which I'll draw it first, and I'll ask you what it is. Does anyone know what that is? Hyperbolic, that's the fancy word. There's actually a fancier word and two less fancy words. Yeah.
Saddle.
Saddle. There's one more. Pringle.
What?
Pringle.
The chip?
Yeah. Lobachevskian. I'm not going to spell that. Lobachevskian geometry as well. What's the difference between these two models? This one, if you're at a point and you look up and down, you're always going down. You make a 90-degree turn, you're still going down. In saddle geometry and hyperbolic geometry, you look up and you go down. You make a right turn, you're not going up. So it's like instead of being like this, it's like this, right? Versus like that, right? So now, if you've given a line L and a point P not on L, there exist infinitely many lines through P parallel to L, and the definition of lines in hyperbolic geometry satisfies hyperbola. Those all count as lines. Those are all lines. So in fact, there's infinitely many lines. And in fact, if you were to embed a triangle on anything saddle-like, the interior angle sum must be strictly less than 180 degrees. Right? It's in fact the opposite of a circle. The interior angle sum is strictly less than 180 if you have a triangle embedded upon a saddle, right? On such a object. Now, what's the point of this? What I'm trying to say here is that taking the negation of the parallel postulate does not prove an inconsistency. What it does do is prove three distinct models of geometry. Now, mathematically, it is interesting, fine, whatever. You have different axiomatizations of different models. But philosophically, this is really not good. Why? What is truth? I mean, this is, again, a concept hard to define. We all know what it is. And philosophers have argued, perhaps incorrectly, for millennia about what the notion of truth is and its responsibility. Specifically, people like Kant and Spinoza used notions of Euclidean geometry. They didn't call it that, but they used notions of Euclidean geometry as a kind of knowledge which is not learned, but is universally understood. So they made treatises and so on, and they were arguing about that there are certain principles which are not learned from your parents and your teachers, but are understood to you in a prior sense from the day you were born. So some amount of information that you walk around with is already in your head, independent of the system that you were raised in. The way we experience geometry in the Euclidean sense is their canonical example of this, of a kind of knowledge which is not learned. But the problem is now like, truth is not then universal. It is not something which is absolute and given through God. It is not into totality, it's not perfect, because you can have alternative models of truth. There are alternative truths, and today we would say something like truth is not absolute in any sense, but in fact relative to the set of axioms. And what axioms you work under, in fact, define what your truth is. It is not the case there is a single model of truth for all of math, and that everything is true in the same model, but depending on which model you have, your truth may be dependent upon those axioms. For example, not only is it true that you can construct a triangle of greater than 180 degrees in spherical geometry, you can in fact not construct a triangle of 180 degrees in spherical geometry. So the fact that there exists a triangle of 180 degrees is cannot be done in spherical geometry. In fact, we can prove that a triangle of 180 degrees exists if and only if the fifth postulate is true. So sometimes you can actually take as the fifth postulate the existence of a triangle of 180 degrees. If that's true, then you have Euclidean geometry. So importantly was not the fact that three models or whatever, but the fact that they were non-contradictory is the significance here. That's very bad. And basically, this was a crisis. This totally erupted what proof was. And like, what does it mean to demonstrate something? What does it mean for something to be true? What does it mean for you to prove something? These are all notions that had been used for millennia and were kind of like vaguely understood. But such a crisis meant that we need to look at such questions more carefully. And it is because of this crisis that logic was invented. So we need to take a more careful look at what is a theorem, what is an axiom, what does the axiomatic method mean? And so it was not the case that Euclid's elements were just like thrown away because of this, but it's understood that, Euclid's elements still take the fifth postulate, but it's not necessarily true that they are a universal and the only truth, because there are other truths. Right? Questions on that so far? Let's quickly prove that you can construct a triangle of 180 degrees given the fifth postulate. And just to show you an example of what proof in Euclidean geometry may look like. You guys do Euclidean geometry in high school? Such constructive proofs? So this may be familiar to you. Okay? We will prove that the parallel postulate implies there exists a triangle of 180 degrees. And what is really 180 degrees? It's half a circle. Now this is actually an if and only if, but the reverse direction is quite difficult, so I'm just going to leave it at this one. First, construct any triangle. Let's call it A, B, C. Okay? Next, we may apply, I forgot what axiom it was, maybe the second one. We may extend the line segment BC off in such a way. Okay, let's call this point, I don't know, D. Construct a point E such that EC is parallel to AB. Let's call this E. So we want it to be the case that the line AB is parallel to EC. Okay? Now, what do we know by the parallel postulate must be equal to? What is this angle equal to?
The angle between AB and BD.
Let's say ABC, but that's correct. So we know then that these two angles are equal. So we know that angle ABC is equal to angle ECD. And that follows from the parallel postulate, right? In fact, the construction of E through C being parallel to AB follows from the parallel postulate as well. There exists exactly one such line. What do we know about this angle? Angle ACE. BAC. Okay. Now, what about this one? It completes two things. First off, it completes the triangle. So this plus this plus this is the interior angle sum of triangle. This plus this plus this is exactly half a circle. It's the pi radian, so it's 180 degrees. QED, this is, I should do this plus this plus this, then substitute this plus this, and then whatever. But we see that the interior angle sum of the triangle is 180 degrees, right? This is such an example of a proof in Euclidean geometry. It must be more formal, and it must specify which axioms are cited, and so on. But notice how it really depends on the parallel postulate, right? We would not get the equality of these angles were this true. In fact, we would get something much worse. Suppose that there was infinitely many lines through here. There could be a line like this, and perhaps even a line like this. And then you would not get uniqueness of either of those two angles. Questions on that? Okay, let's talk quickly about So the crisis in geometry erupted, and people started arguing about what truth meant. And similarly, we also were arguing about like the role of Cantor's theorem with respect to truth, because some people were still taking Cantor's theorem as something that should be false. So what came out of this was roughly 4 schools of what is the role of mathematics with respect to logic and proof. We have formalism, logicism, intuitionism, and we also have linguisticism. Not linguicism, linguisticism. So let's talk briefly about what these sort of, people started demarcating themselves into different camps based on these such results, and this influenced the development and the history of logic. So formalism was pioneered mostly by David Hilbert, and he argued that axioms and theorems should be meaningless, and that they should only follow sort of manipulation as that of a chess game. So for example, consider when we do some sort of proofs. For example, let's say we take f of x and we evaluate it at 3, right? Let f of x, for example, be x squared plus x plus 1, something like this. When we plug in 3 here, in a very symbolic and literal sense, f of 3 is then what? 3 squared plus 3 plus 1, right? So what is really the point of evaluation? Evaluation is done in a string manipulative sense. He didn't know what a string was. But in a purely symbolic sense, the symbol for x has been literally replaced with the symbol for 3. In the sense that there are sequences of rules which the rules manipulate the symbols, and the symbols are completely meaningless. They just happen to correspond to notions of mathematical intuition, but they are, you could not, for example, take a derivation as a step in a theorem according to some greater intuition about how that object ought to behave. But it must follow from pure symbolic manipulation of the symbols. This is formalism. This is like Hilbert's version of formalism. And he makes this analogy of a chess game, right? And such philosophy would end up influencing the development of grammars, because what is a grammar if not just a string writing and rewriting system, right? So it was kind of obvious that this is, for example, if x is some non-terminal, we could have a production of the form x goes to 3 for whatever constant we may want there, and then substitution would proceed, right? We may also have rules of the form x 3 squared can be transformed into 3 times 3. And then there may be rules for simplifying the multiplication down and so on, right? Consider some of the basic rules of logic. We may have, like, for example, double negation. We may have De Morgan's. But if you think about these, like, for example, De Morgan's, let's say not P or Q is equivalent to not P and not Q, right? This is nothing but a manipulation of symbols, in the sense that in a very physical sense, this negation just goes through, right? The symbols have weight, but they don't have meaning, right? This is formalism. Logicism was pioneered by Russell and others, and it's basically, it's almost identical to formalism, to be honest. But logicism basically says logic is the strongest and greatest tool of all of mathematics. It's like all theorems of math may be taken as theorems of logic. So, I mean, this is maybe something you believe today, in the sense that logic is the backbone of all mathematics. When you do a proof in mathematics, it is understood that in this class we've done many proofs, we've done many paragraph proofs, but the difference between math and logic is exactly the same difference between programming and assembly, in the sense that logic is what controls truth, and that given a proof, if some portion perhaps is not intuitive enough, then it maybe need to may need to be compiled down, quote unquote, to assembly, right? You may need to specify the logic a bit more, in the same way you may inline assembly. So, and it is the case that every theorem in mathematics, all of it may be taken as theorems of logic. So logic is pure logic is the backbone of all of mathematics. It is the granite foundation. I'm thinking if there's anything else I need to say about that. Any questions on those two? Okay. Intuitionism, this is a kind of a tough one. And intuitionism, and is sort of a totally rejection of the previous two theorems. The previous two schools of thought, and it went to war with them. Intuitionistic logic is more of a fossil than any sort of modern belief system, and nobody really believes it today except to be contrarian. Intuitionism is, Intuitionism is this, there's several points to it. Intuitionism. The first is that many theorems of logic are, it doesn't make any sense to found mathematics on logic, because what are theorems of logic if not also theorems of math? So you get some sort of circular issues going on because you may have theorems of logic to be proven with theorems of math. For example, there are some things you can prove in logic using the Chinese remainder theorem. But is the Chinese remainder theorem not a theorem of logic itself? So is there not a circular argument to be made here by taking logic itself as a foundation for math when the theorems of logic are themselves math? So the first thing is that logic cannot ever be, you can never have a strong foundation of logic to underpin mathematics. And that in contrast, they offer mathematics purely in the intuitionistic sense, an act of creativity. It must be something that is artistic. And they view attempts at logic as something that sanitizes and makes formal and ugly notions of things that are supposed to be beautiful. And think about how we do proof, right? So what happens with proof is we make certain statements. There's a game that is played between the reader and the writer, in the sense that if I'm doing the proof on the board, for example, I make a very small jump, and then you believe it. And then I make another small jump, and then you believe it, and so on. And this is the interaction between the reader and the writer for the proof. Now, if the writer makes too big of a jump, a formalist or a logicist would say, okay, that maybe needs to be explained more, compiling down to logic. The intuitionists don't really care about this. And it is the case that the proof must be done appealing to most really basic principles, but not necessarily ones of logic. People who believed in this were Brouwer. Have we heard the name Brouwer in any context?
Fixed point theorem.
Brouwer's fixed point theorem. I don't think the fixed point theorem is in fact intuitionistic, and he spent a lot of his life and lost a lot of his career by backing such a school of thought. There's also Poincaré. Poincaré also rejected logic, and because he viewed it as this limitation on creativity. And if you think about it, that kind of makes sense, because people in logicians are as annoying as people whose favorite programming language is assembly, right? They are, I won't say uncreative, but they are very, they're sticklers in a way that maybe they don't need to be, kind of thing. And this sort of restriction is kind of arbitrary. The second thing about intuitionism is that they reject the role of non-constructive proof. So, and this kind of, some of them would perhaps reject Cantor's diagonal argument. But suppose you want to prove some statement for all x, some predicate phi of x is true, right? Or perhaps prove that it is false. What you would prove instead is that there exists some x such that not phi of x, right? If some theorem is false for all x, then there must exist an x that it is false for. If some theorem is not true for all x, then there exists some x that it is false for. Intuitionists, they would reject this immediately. And in the sense that the proof of such a statement must be demonstrative, in that you cannot demonstrate, there are many proofs, and we'll do one today, where you may demonstrate the existence of an object without actually knowing what the object exists. Now, quantification like this over finite sets they don't care about, because the search exists for x in principle. But if x is quantified over an infinite set, let's say natural numbers, then this is not, they would not like such a proof. The proof must demonstrate the existence of the object and not demonstrate, and without saying it exists, without actually knowing what it is. They have to know what the object is. Proof must be constructive, right? Maybe I give us an example of a non-constructive proof before we proceed. Let, the proof we can use is there exists irrationals, a comma b, such that a to the b is rational. Have we seen this before? I've done this one in 2050, I think. There exist irrational numbers, a and b, such that a to the b is rational. So this is not like a particularly important theorem, but it is an example of a non-constructive proof, and it is a proof that we should all believe, but intuitionists would reject. So let me give you the classic example. So we have two cases. Case one, square root of 2 to the square root of 2 is rational. Case 2, square root of 2 to the square root of 2 is irrational. Those are the only two cases we have, okay? Notice the cases are total in that square root of 2 to the square root of 2 is either rational or irrational. We don't actually know which one it is. I know which one it is, but we don't know which one it is in context of the proof. But it's one of the two. Certainly it's either rational or irrational because every real number must be rational or irrational. Okay? So if square root of 2 to the square root of 2 is rational, let a equal b equal the square root of 2. Thus, square root of 2 to the square root of 2, a to the b, is equal to the square root of 2 to the square root of 2, which is rational. But a and b are both irrational. Why square root of 2 is irrational is known, and I've proven that in 2050. It's a classic proof. Nemesis, right? Pythagoras killed him, something like this. Second case, what if square root of 2 to the square root of 2 is irrational? Well, let a equal square root of 2 to the square root of 2, and then let b equal square root of 2. So a to the b is then square root of 2 to the square root of 2 to the square root of 2, which is square root of 2 squared, which is 2, which is rational. Therefore, there exists a comma b such that a comma b irrational, such that a to the b is rational, QED. Now notice, importantly, we have demonstrated the truth of the theorem. We don't know an example of, we don't know what a and b are. It is one of the two cases. It must either be square root of 2, or square root of 2 to the square root of 2 and square root of 2, okay? One of those pairs of numbers, this theorem is true for, but we don't know which one. So this is an example of a non-constructive proof because we have demonstrated the existence of an object, but we don't actually know what the object is. Intuitionists would not accept this proof, as they would reject such a proof. They do not value the role of non-constructive proof. Another important thing, they even, to some extent, reject laws of double negation, right? If something is not false, it is not necessarily true. If you can prove that something is not false, it is not the case that it must be true, because you have not demonstrated its truth, you have just demonstrated that it is not false. And they split a hair there between those things. Now, if something is not false, it must be true. Why? Does anyone know the name of the law? So what is the notion of truth exactly? Everything in this world either is or is not, to be or not to be. For any such proposition, it is true that this is a tautology, right? Do we know the name of that tautology? So what is the relationship of truth? Things are true. There are things that are not true. Is there anything else?
Fuzzy logic.
But we're concerned with truth in the absolute sense. If something is maybe true, it is false. Truth is absolute, especially in the context we're seeing of. There are many other logics that try to work with different definitions of truth. They're all useless. They're all sort of toys, and none of them actually demonstrate anything with any amount of certainty. We are concerned with truth in the absolute sense, so that's fake. Yeah?
Moore or De Morgan?
More De Morgan?
Well, I know Moore's law has to deal with Boolean operators like that.
But we're prior to some notion of circuits in computer science, in fact, because those are taken as terms of, in a strong, I'm asking, I guess, in a strong philosophical sense. Not why is this true, why is this a law, but I'm saying why is it a good law? They must be, every rule that we have must be grounded in our intuition, in the sense that we take samples of the human experience, and the law is as we say it is because it makes sense. I guess it's kind of one of those, back to those, it's obvious kind of things. It's true, so that's it. Aristotle wrote extensively about this. Is called excluded middle, the law of excluded middle. And intuitionists would reject excluded middle, especially over infinite sets, because something not being true does not mean that it is false. Excuse me, if something is not false and is not the case, then it must be true. But this is such a basic axiom that everyone takes this, right? This is certainly to be believed. I have a quote by Avicenna here. Avicenna was like a 11th century Muslim scholar and he wrote commentary on Aristotle's metaphysics. And Aristotle discussed this extensively. There cannot be something between contradictories, right? So here's the quote by Avicenna. As for the obstinate, he must be plunged into fire, since fire and not fire are one. Let him be beaten, since suffering and not suffering are one. Let him be deprived of food and drink, since eating and abstaining are one. So it is such a cognitive prior, pre-scientific notion that it cannot be disagreed with. But yet intuitionists demand that proof must be constructive, and demonstration of an object has to come in a direct way, not in a way that but you cannot demonstrate something by showing it is not false. You must demonstrate its truth in a more pure sense. Two last things I can say about this is that Poincaré was a really good mathematician. You've heard his name probably in other contexts with respect to the Poincaré conjecture and notions of geometry and things like this. And there was a psychological study done on Poincaré by one of his contemporaries. And they were like, okay, yeah, his brain's like wired differently. He just like doesn't get it, but he is able to get other things. So he was really good at proving stuff. And there's some quote that said something like, he doesn't climb mountains, he just jumps from peak to peak. So he's immediately able to go from point to point. So it may be the case that these guys had a different cognitive architecture that intuition worked for and that logic could never. But the rest of us have to deal with logic, something like this. Right. Questions on intuitionism? Important, also, I'm pretty sure intuitionism, they would reject Cantor's diagonal argument. Intuition was mostly abandoned because people tried to construct sets of axioms that model intuitionistic thinking. Intuitionists would reject such a system, and in fact, there's a system called Brouwer-Hating-Kolmogorov that Brouwer, who the system is named after, rejected the creation of such a system, but anyway. And basically, you can prove most things in intuitionistic logic, but there are specific theorems that appear to be missing, that do not have intuitionistic proofs. I don't want to talk about such results, but it is the case that it just appears like there are things that you can not do intuitionistically, we just don't know how to do them. It's certainly a subset of things that are provable, because if you have an intuitionistic proof of something, you have a normal proof of it as well. Because we don't reject intuitionistic proof, they reject some things that we accept. Something like this, right? It was abandoned simply for the fact that it was like some famous 20th century people who were carrying the flag about this were like, okay, actually, in practice, it's just not useful. So they converted, quote unquote, converted simply because it was, I mean, it's not as useful. In a very practical sense, it's not good. Philosophical considerations aside, normal logic is far more powerful than intuitionistic logic, so join the bigger camp. Any questions on intuitionism? Linguisticism is the last one, and it is really insignificant and important. Has anyone heard the name linguisticism? Has anyone heard the name Wittgenstein? Wittgenstein is the only guy who championed linguisticism. He wrote this treatise called the Tracticus, and basically he argued that it is impossible to do logic, but his concerns were with the externalization of ideas. And he wrote this treatise basically because like language is too important and it cannot be formalized in any notion. Since the meaning of words can never be made absolutely precise, it is impossible to have any kind of deductive proof be absolute. And any kind of attempt at logic is just playing pretend, so to speak. And if you cannot he really considered the role of language more than anything in logic. I think the most famous quote from his treatise is something like, that which we cannot speak about, we must pass over in silence. So only things that may be deduced are those which may be expressed in language. Something like this. No one cares. It's just sort of his own little guy over there. So, questions on this? All right, let's take a break. We'll talk about logic after the break.